All right, guys, today we are going to go through the notes that you would have gotten in class if I were there for Unit 7, Day 1. And we are going to talk about confidence intervals again, but this time we are going to do it for means. So you should only be watching this video if you have already completed your Unit 6 test, meaning you took it last class, or you finished it today, and you are now doing this for the rest of the class period. If that applies to you, great, wonderful. If that does not, then go home and do this video for homework and finish your test first. So our context for today is trying to estimate the true mean weight of an Oreo, of all Oreos. And based on the package, it says that a serving size is 3 cookies and it should be about 34 grams. We took a sample of 30 cookies and found that the mean weight of the sample was only 11.19 grams and it had a standard deviation of 0.08 grams. So we want to create a 95% confidence interval to estimate the true mean weight of all Oreos. Just like before when we did this for proportions, we are going to use the idea of a point estimate plus or minus the margin of error. But this time, our point estimate can't be a proportion. Last time it was p hat. Today, it is going to be x bar. And x bar is the sample mean. So in this case, it is 11.19. The difference between means and proportions is that means have units. A proportion, we just said it's 0.115 or whatever, but here it's 11.19 grams. So we're going to use that idea of means having units throughout our lesson today. Hopefully you can fill out, based on the information you've been given, the population, the sample, what parameter it is we're looking for, and the statistic. So if you want to pause the video and attempt that right now, that would be lovely. But if you're just pushing play and continuing on, then we would have the population being all Oreo cookies. Our sample is 30 cookies. They gave us the statistic that x bar is 11.19 grams. And our parameter is no longer p, because we're not looking for a proportion, we're looking for the population mean. And the symbol for that is mu, the true mean weight of all Oreos. And we're going to look for it in grams. Just like before, you can look at the prompt. True mean weight for all Oreos. Hey, look what we have. True mean weight for all Oreos. It should go together. They should be the same thing. So you should be able to answer questions 3, 4, 5. If you want to try those yourself, I fully support that. I think that is a wonderful idea. I think you will learn more by doing it that way. Do it in pencil. You can always go back and you can change it. Or you can just keep watching the video and I'm about to do them. But I would really strongly suggest you try them on your own first. So question 3 says, was it a random sample? And it says, yes, it is a random sample. How do we know? It tells me we had a random sample of 30 cookies. So I'm going to quote that prompt of 30. This part, why is that important? You don't have to write this on the AP test. When it says, did you meet the random condition? You just say yes because it's a random sample. This is for our understanding. It allows us to generalize our sample results to the population. That means that our sample is a representative sample. Because it was random, we can say that the values we found in our sample are going to be true across the population. So we know that the formula for the standard deviation in means, for a mean of sampling distribution, is that sigma, over root n. We talked about before, as your sample size gets bigger, the standard deviation of your sampling distribution will get smaller. And in order to use this condition, we need to meet the 10% condition. So we need to say that our sample, which in our case is 30, needs to be less than 1/10 of the population, which in this case is all Oreos. So we're going to set up the formula for standard deviation, but the problem is we don't know what sigma is. We don't know sigma, so we use our best guess for it. Instead, we're going to use S over the square root of n, which means this is no longer the standard deviation of a sampling distribution because we've kind of fudged some numbers. So we call it the standard error, and it's the standard error of X bar, which makes for a really interesting acronym there. One most people don't forget. So we put, in this case, 0.08 over root 30, and this 0.08 number came from our prompt. This is S from prompt. And this is our sample size. We had 30 cookies. So we find a standard error of 0.0146. And the last question says, would it be appropriate to use a normal distribution? Well, we knew that for proportions, we were using the large counts condition. We needed n times p and n times 1 minus p to be greater than or equal to 10. We don't have that here. So we had two ways in the past to determine if the sampling distribution of sample means is going to be approximately normal. One option was the population is approximately normal. Well, we don't know anything about that. And the other one was the central limit theorem. So the central limit theorem says, as long as your sample size is greater than or equal to 30, your sampling distribution will be approximately normal. So in this case, we had a sample of 30 exactly, so we are good. So yes. Then we now have everything that we need in order to create our confidence interval. We need the point estimate, we have that. We have the standard deviation, but in order to turn it into a margin of error, we need a critical value. Because remember last time we had our point estimate plus or minus Z star times the standard deviation. With means, we don't use Z. This is where it gets weird. We use something called T star instead of Z star. In order to have a normal curve and use Z, you have to know the mean and the standard deviation of the population. We don't know the standard deviation of the population, so we cannot do this. We cannot call it a truly normal curve and use Z-scores. A normal curve looks like this, and we know that 95% of the values are within 2 standard deviations. A T-curve gives more of the weight to the tails. So this is a T-curve. The blue one here is a normal curve. T is more forgiving. It gives us more flexibility. It gives us more room on the edges because we're just not sure. We have more things going on now. We used to have Z equals X bar minus mu over, here was our formula. But the issue is since we don't know sigma, we're using S. That increases the amount of things that are varying. That means I need more wiggle room on my tails. So I don't call it Z, I call it T, and we're going to use the inverse T function on our calculator to find our critical value. That's a lot of complicated words to say. When we do proportions, we use Z-scores. When we do means, we use T-scores. So I'm going to use a degree of freedom, tells me how much wiggle room I want to include in this. So my degree of freedom is n minus 1. So in this case, the degree of freedom would be 30 minus 1. I would have 29 degrees of freedom. And it's important to note that as the degrees of freedom increases, the distribution, the t distribution gets closer to a normal distribution. So 29 degrees of freedom is pretty good. The t-score and the z-score won't be that far apart. If you have a really small degrees of freedom, then there's a lot more variability or variation between your z and your t. So we're going to go on the TI, and on the TI, you go to second vars, and you're going to choose inverse t. The inverse t asks you for two things. It's going to ask you for the area. Well, since this is a 95% confidence interval, the area on the edge would be 2.5%. And it's going to ask you for the degrees of freedom. And that will give you a z-score of 2.045. So it actually gives it to you as a negative, but we know that it's a mirror image curve, so take the positive. Your equation has plus or minus in it. It doesn't really matter, but we're going to use the positive version. So for a 95% z-score, we know this would have been 1.96. So we're at 2.04. Like, it's very similar at this point, but it is slightly different. All right, so now we have our t star value, and we can calculate our entire 95% confidence interval. Okay, sorry, I'm adjusting. Do you like my Dude Perfect book underneath of here? So we have calculate the margin of error using t star and the standard error. Okay, so the margin of error is your critical value times the standard error. So in this case, we have our t star times the standard error is s over root n. We just found t star is 2.045. And we know that this is 0.08 over root 30. So when I multiply that all together, I get 0.03. So my 95% confidence interval, point estimate, we said that's going to be our x bar. Margin of error is what we just came up with. In this case, it was the 0.03. So we have 11.19. That was the sample mean we found, plus or minus 0.03. Our final interval becomes 11.16, 11.22. Interpret the interval is exactly the same as it is for proportions. There is zero difference. This is just a script you need to memorize. We are 95% confident. The interval 11.16 to 11.22 grams. We need units here. Means have units. Captures the true, and then this is where, true. This is where we go back to what we defined at the beginning. We called it the true mean weight of all Oreos. So we're going to say exactly that here. True mean weight of all Oreos. Grams. Okay. So our formula for this confidence interval, for mean or for proportions, we had a different formula. It was still point estimate plus or minus the margin of error. But now our point estimate is x bar plus or minus the critical value times the standard error, which in this case is s, the sample standard deviation, over the square root of n. According to Nabisco, the average weight of an Oreo is 11.33 grams. Do we have convincing evidence? The true average weight is different. Different, not less than, not greater than, but just not 11.33. So based on my interval up here, I would say yeah, because my interval doesn't include 11.33. So I will say yes, 11.33 grams is not in our interval. And then it says explain, so I would say all plausible values are less than 11.33. Right? The max number in our interval is 11.22. Okay, so now there's a couple practice questions down here. The first one is just, do you know how to use your calculator? So why don't you pause the video and try. Can you find what the t-star value would be? This is just using inverse t for a 98% confidence interval with 26 observations or a 99% with 85. And if you do it, you did an inverse t. Your area would be 0.01 because 98% is in the middle, so 1% in each tail. With 25 observations, that gives you 2.485. And here, if I did an inverse t, it would be on 0.005. 99% is in the middle, so 0.5% on either side with 84. It's always the number in your sample minus 1. And that gives me t star equal to 2.636. So what are these points? This is the area, and this is the degrees of freedom. Area, degrees of freedom. All right, and the last question, it says, have the conditions for constructing a confidence interval been met? I'm looking at, what is this? Each person reported how much they or their significant other spent on an engagement ring. Oh boy. You can clearly see this graph is very skewed to the right, right? Strongly skewed to the right. Oh, you can't see because I covered it up. There we go. Strongly skewed to the right. But we have other ways to check these conditions. So there are 3 conditions. The first one is random. The second one is 10%. And the third one, instead of calling it large counts, we're going to call it normal / large sample. Because we can either meet it by saying the population distribution is normal or we have a large enough sample. So pause, fill this out, prove why we have met all 3 of these conditions, and then hit play and go over it. So I think it's random because they said it's a random sample of 1640. I think it is sampling without replacement, so we need to check the 10% condition. But I would say 1640 is clearly less than 1/10 of all adults. And for normal or large sample, it's not normal. We just talked about that. It's very skewed, but 1640 is greater than or equal to 30, so we have met the central limit theorem. Okay. All right. Let's formalize this in think, plan, or sorry, that was old. Choose, check, calculate, conclude. Okay, sadly, we don't get to do this activity together. I would have loved to have you guys look at your phones and find your average screen time. So instead, we're going to use the data that I collected from classes last year, which I think will be slightly higher than yours. I hope at least, since phones got banned this year. But it'll be interesting nonetheless. So last year, the class that I recorded had 31 students. In that class, the average amount of screen time was 408.2 minutes, and the standard deviation was 146.5 minutes. All right, so it is spread out for you, the choose, check, calculate, conclude. I want you to try and do the choose and the check. Pause the video, do the choose and the check, and then come back and check your work and see if you got it. Do it in a pencil. You can erase it. There's no pressure, but try. Like legit, if you don't try, you're not gonna learn. You don't learn by copying. Do it yourself and then come back and check it. Okay, so for the procedure, we are gonna call this a one sample, because that's all we have. We have one sample of data. This is it. T, it's not a Z anymore, it's a T interval for mu. We are running an interval to calculate a mean. What does that mean? Mu is average screen time for all AP Stat students. So we're going to say true average screen time for all AP Stats students. And our confidence level, it told us that in the problem, 95%. Check. We know we have three conditions: random, 10%, and normal/large sample. So random, it's not truly a random sample, right? Like, is one class of AP Stat students representative of all? Probably not. But we can't do much if it's not random, so we're going to kind of fudge our way here. And we're going to say, consider the class a random sample. I promise you on the AP test, everything will be clearly labeled as a random sample, if that is the intention of the problem. 10% is clearly met because 31 is less than 1/10 of all AP Stat students. And I don't know anything about the population, but I do have a sufficiently large sample. 31 is greater than or equal to 30, so we have met the central limit theorem. You don't need to write what I'm doing in red on the AP test. This is for our understanding of what's going on here, but why we do each of these things. And I know we've done this a million times. I know you're like, well, duh, I already know that. Great. That's the goal. If you're still struggling to learn this, write it down. This allows us to generalize to the population. So we can say, hey, the values that we found in our sample are going to hold true across all AP Stat students. The 10% condition allows sampling without replacement. And the normal/large count says that our distribution will be approximately normal. It's not quite, and we're going to use T instead of Z because it's really not quite, but close. Okay, and then we calculate. So our formula is point estimate plus or minus the margin of error. This is the same whether we're doing it for proportions or means. But with means, our point estimate is X bar. Our margin of error is T star times S over root N. So they gave us all the numbers. Here is our sample mean. We do need to find that T star. They didn't give us that, so we're gonna have to do an inverse T here. It wants it to be 95% confident, so my area would be 2.5%, and my degrees of freedom would be 31 minus 1. So this is degrees of freedom is n minus 1, and this one is my area. And that gives me 2.042 as my T star. And I can multiply that by the rest of this. S 146.5 over root 31. And you can plug that in your calculator and you end up with 354.5, comma, 461.9. The cool thing is you can also do this on your calculator. So on your calculator, you can get this by going to Stat, Test, and choosing number 8. It is called T-interval. Looks like it's saying tinterval, but it is not. It is a T-interval. So you don't actually have to show all this work. You have to do the choose, the check, and then you are welcome to go straight to this answer if you pull it off of your calculator on the AP test. That is legit. You're still going to need to know how to find the T-star. It very much could show up in a multiple choice question. You very much could need to plug in pieces and parts to a formula or use it to work backwards to solve something, but you don't need it for the free response. And then conclude. Conclusion is the same as it's always been. Pause the video, write your conclusion, come back and check and make sure you got it right. We are 95% confident the interval 354.5 to 461.9 minutes. You have to have units here. Captures the true, and I'm going to take it straight from the prompt. The true average screen time. I'm going to use the word mean because that's what we were looking for, but you could say average. Screen time for all AP Stats students. All right, then the CDC recommends that teens spend a maximum of 120 minutes on their phone per day. Based on my interval, what are we thinking? We got this interval, 354 to 461. CDC says we should spend 120 minutes. Do we have convincing evidence AP Stats students are having more screen time than recommended? Yeah. 120 minutes is below our interval. All plausible values are higher. Get out your phones, guys, as I tell you to watch a video that is more screen time. Oops, sorry. All right, last page. Practice. We're going to run a full confidence interval. So I would do this bits and pieces. I would say, all right, let's start. We're going to do the choose. We will do choose, check, calculate, and conclude. Just do the choose. See if you can flip back to what was required of this in the last problem and write the pieces for choose. Pause the video, do the choose, come back to it. So for choose, we needed to name the procedure. We're going to call it a one sample T interval for a mean. Why? Because we are trying to find out the average amount of garbage in the community. We found one sample of a bunch of households, how much garbage they had. So we are looking for mu, the true mean weight of garbage for all households in this community. Mean weight of garbage And we're gonna give it a unit because it's a mean. It tells me that it's in pounds. Pounds for all households in this community. And the last thing we need is a confidence level. So the confidence level here is 99%, so I'm gonna put 0.99. Okay. Awesome. All right, check. Put down your 3 conditions. You're gonna be able to check the first 2 easily. The third one, come back and we'll do the third one together. But you should be able to do the first 2 checks. So pause, do them, push play. Our first one is that it is random. It tells me random sample of, I should finish this, of 15 households. Ta-da. Second one, 10%. 15 is less than 1/10 of all households. You just have to assume it's a pretty big community. I think that's reasonable to assume. The last one, for normal / large sample. Well, I don't know anything about the population, so I can't say that the population is normal. I don't have a large enough sample. 15 does not meet the central limit theorem. So this is where we get super fuzzy and we kind of blur the lines a little bit. If you don't know anything about the population and you don't have a large enough sample to meet the central limit theorem, we are going to go to the most wishy-washy way to meet this condition ever. We're going to plot all of our sample data and we're just going to say, is there anything weird going on? Is there a really strong skew, or are there any crazy outliers that are going to mess with our data? No, I mean, it's all spaced out pretty evenly. There's nothing weird going on. So we can meet this condition by saying dot plot shows no strong skew or outliers. That is not our first choice of ways to meet that condition, but it's our last ditch effort. We don't have much else to go off of. So now I'm going to calculate. Do it on your calculator. See if you can find the interval before I put it down. Pause the video, use your calculator, find the interval. You should use stat, test, and choose number 8. You put in all the info and it gives you an interval of 38.59, 80.41. Why is that such a huge interval? Because our sample size is really small. And because if you look at your t-star for this, the t-star value ends up being 2.977. It's a really big t-star because our sample size is really small, so we're going to be out in those tails, and it's a pretty big number. It's a 99% confidence interval with a small sample, so we have a really, really wide interval. But again, you don't have to write this. This is the piece that is absolutely required. Okay, and you should be able to write a conclusion. We are 99% confident that interval from 38.6 to 80.41 pounds captures, and then we're going to put the parameter here. The true mean weight of garbage for all households in this community. Okay, so there we go. That's our lesson. It should feel fairly similar. It's a lot like what we did for proportions. We're just modifying it slightly for means. So to summarize, in the choose section, you need to name your procedure. We're going to call it a one sample t interval for mu. Define our parameter, that's mu, and identify the confidence level. We're going to do our 3 checks. For random, we need to make sure we have a random sample. For 10%, n needs to be less than 1/10 capital N. But this is only if sampling without replacement. And for normal or large sample, we have 3 possible ways to meet this condition. Either the population distribution is approximately normal, or the sample size is greater than or equal to 30, that's your central limit theorem, or the sample data shows no strong skew or outliers. That's a wishy-washy way to meet it, but in a last-ditch effort, we'll do that. For calculate, we're going to do, it's the point estimate plus or minus the margin of error. Same thing it's always been, but now we have x bar as our point estimate. We're using t star as our critical value, and our standard error of x bar is written like this. We can also find this by going to stat, test, and choosing number 8. For conclusion, we are blank % confident the interval from blank to blank captures the true, mean, whatever the heck we're talking about, context, and we're going to include units. Summary here, Z stars for proportions. We're not doing proportions this unit, we're doing means. So T star is for means. And the degree of freedom is n-1. You have some words here. They should have been deleted. Erase them. The thing about always round, don't round. Cross it off. That's not a thing. Bye-bye. We made it. 37 minutes. Okay, that's awesome. You're done. You have no homework. This is it. Congratulations, you finished. Yay. See you on Friday. Bye.